So I'll just talk a little about what we are doing here at UMass Dartmouth in our group, working on thermonuclear type 1a supernovae. And we have a lot of members currently, including some SPS members. I think Ian, Logan, and Mackenzie, William, Alex are all members of the group currently. And of course, we're always interested in working with new talent. So I'll start off with just showing a really an overview of the evolution of a mass, a star like our sun, one solar mass. And here we can see the evolution in time as a star like our sun burns hydrogen, moves up the red giant branch, and eventually it reaches a point where it's burning hydrogen in an envelope surrounding the core of largely depleted hydrogen and some helium. And at that point, as it moves up the red giant branch, and you'll see these circles are meant to denote lines of constant radii, so the star is swelling outward. It starts to burn helium inside the core, becomes a horizontal branch star. We'll see this in a moment. And then as it starts to burn helium in the core, it's producing through a reaction known as the triple alpha reaction, 3 heliums going to a carbon nucleus, some carbon and oxygen in the core, which is basically a degenerate, well, we would say an electron degenerate core, which is supported by the weird physics of quantum pressure. And that is basically a nascent white dwarf. And here we can see the evolution into a second branch, a second giant phase, which is called the asymptotic giant branch phase. And ultimately that star moves over and becomes this small, compact, degenerate object known as a white dwarf. And these white dwarfs can be produced in binary systems. And you can think of them a little bit like charcoal, right? Charcoal is something, wood, which is burnt, but hasn't completely depleted all of its energy. It's a source of additional burning energy that's possible when you burn the charcoal. So the white dwarf has carbon and oxygen, which is not yet at the most stable nuclear phase of evolution, which is something like iron or nickel. And so those white dwarfs can come together in a binary system in a process which is still, quite frankly, not thoroughly understood. But we know that these white dwarfs, when they reach sort of cataclysmic explosion phase, they can explode as these very luminous transits known as thermonuclear type 1a supernovae. And this is a very famous event that's shown here that went off in the year 2011, known as 2011 FE, one of the nearest, brightest, best observed events. And you can see basically on the left panel, the pre-explosion image where there was no source, no stellar source, which was discernible, not even in Hubble deep imaging of that region pre-explosion. After the explosion, there's a luminous transient that has about 10 to the 44 joules or 10 to the 51 ergs in astronomical units that people like to use of energy, which is such a large amount of energy, it's hard to even wrap your head around. It's essentially the luminous energy of that transient is comparable to the total energy output of our sun over its lifespan. So in our group, we're trying to understand how these events originate. So here's a simulation that we're working on right now. This involves 2 white dwarf stars with thin helium layers over their surface. And we can see here's the evolution of the helium as it undergoes an eruption on the surface of the primary. And in this scenario, which is sometimes referred to as a double degenerate, double detonation, well, dynamically driven double degenerate, double detonation. It's a terrible mouthful of an acronym called the D6 scenario, in which ideally this primary carbon-oxygen white dwarf that you can see in the upper right would undergo a full detonation and explode and produce a thermonuclear type 1a. In this transient that we see here, there's the eruption of the helium on the surface, but not yet the eruption of the carbon-oxygen in the core. In this second frame, I'm showing just the helium. And so you can see the dark region in the cores of these 2 white dwarfs. That's the carbon-oxygen material, most of the material of the white dwarf. and this thin layer of helium that you can see on both of the two white dwarfs. And this shows much more clearly how that helium erupts on the surface of the primary and moves on to the secondary, but doesn't undergo core detonation. So this is one thing we're working on in the group. We're working on a whole bunch of different projects at the moment. I'll just